Welcome back. In this lesson we're going to look at conservation of momentum in closed systems before and after inelastic collisions. In a closed system, linear momentum is constant throughout the collision. No outside forces act on a closed or isolated system. I have two carts here, both have the same mass, and I'm going to run them into each other. They'll have the same speeds approaching each other, and we're going to take a look at what happens with this collision. The carts stuck together, so we have an inelastic collision. Let's fill out a momentum chart. In this first demonstration, carts 1 and 2 had the same mass and equal and opposite velocities. We'll give cart 1 2 blocks of positive momentum, which means cart 2 gets 2 blocks of negative momentum. After the collision, both cars were stopped, so they had no momentum. It's easy to see that momentum was constant in this collision. The momentum is 0 at the beginning of the collision because we have 2 positive blocks of momentum plus 2 negative blocks of momentum, which equals the 0 momentum that we have at the end of the collision. For the next demo, I'm going to double the mass of cart 1 and have the same speeds as we had in the prior demonstration. As you could see in this last collision, the cars collided, stuck together, and moved as one massive cart at a reduced speed. Looks like another inelastic collision. Let's chart it. So in this second demonstration, we'll give cart 1 4 blocks of positive momentum since the mass was doubled and the speed stayed the same. Cart 2 still gets 2 negative blocks of momentum. We can see that the total initial momentum is 2 positive blocks. We started with 4 positive blocks of momentum. We added to that 2 negative blocks of momentum, giving us a final total of 2 positive blocks of momentum. We can write an equation under the chart for solving inelastic collisions. So I'll have M1 V1 initial plus M2 V2 initial equals the combined mass of both carts, since they stuck together, times the final velocity. We have M1 V1 initial plus M2 V2 initial equal to the combined mass of both carts, since they stuck together, times the final velocity. So in this demonstration, we're going to have these carts explode, move apart from each other. Cart 1 now has a mass of 2m, and cart 2 has a mass of 3m. Let's see what happens when I depress the plunger. So at the beginning of this demonstration, the 2 carts on the track were not moving, so they had initial momentum of 0. Let's chart it. Let's define our system as both carts in the track. This way we'll keep the force of the explosion internal, and momentum will be constant throughout the collision. We'll take right as positive. We have previously collected data for this explosion. Cart 1 has a mass of 1 kilogram. Cart 2 has a mass of 1.5 kilograms. The combined mass is 2.5 kilograms. The initial velocity is 0. The initial momentum is 0. The final velocities are negative 0.66 meters per second for cart 1 and 0.44 meters per second for cart 2. This gives us a final momentum of negative 0.66 kilogram meters per second for cart 1 and a final momentum of 0.66 kilogram meters per second for cart 2. Our momentum bar chart shows the same results. We start with 0 bars of initial momentum. This time let's change the scale to 0.2 kilogram meters per second per block. So cart 1 has 3.3 blocks of negative momentum, and cart 2 has 3.3 blocks of positive momentum. Notice the ratio of the masses is 2 to 3, and the ratios of the final velocities is 3 to 2. The equal and opposite internal forces are applied for the same amount of time. So each cart has the same magnitude of momentum after the explosion. Momentum is constant before and after the explosion. You can think of an explosion as a collision in reverse. You'll use these ideas in the activities to follow.